Okay, so good morning everyone. I'm Piyush, I'm from the Computer Science Department at IIT Kanpur. So I believe this is the last day of the workshop. I wasn't too sure what topic to talk about, so Raghu basically left it to me. So I just found out what topics have been covered. Yeah. So I believe you have seen linear models for prediction. Okay. So what I thought would be probably of interest to some of you, or maybe most of you, would be to how to turn linear models that you all very well know about into nonlinear models. Okay, so how can we compute, like, let's say, learn a nonlinear function that maps some input x to another output y. Okay, have you seen kernel methods in this workshop? But I'm not sure in what level of detail. So what I'm planning to do in this session, these 2 hours, is that I will try to talk about two ways of turning linear models into nonlinear models. The first way will be the first hour of the talk, where I'll talk about kernel methods in some more detail. So I'll show how kernel methods can be used to learn nonlinear models. And then in the second half, and also depending on the time, I will talk about how we can use deep learning techniques to learn nonlinear models. So I believe deep learning has not been talked about in this session. But again, 1 hour is probably not that much time, but I'll still try to cover the overview of what deep learning is about. So primarily, these 2 sessions will be, the first one will be on kernel learning, kernel-based methods for doing nonlinear learning. The second session will be on using deep learning methods to do the same thing. Okay. So again, without much further ado, let's get started. So again, how can we turn linear models into nonlinear models? Okay. Well, linear models, as we all know, they are simple and nice. If you have like a linear structure in the data, you can easily learn models for regression like linear regression, or if you know things like logistic regression or linear SVMs, you can learn classification boundaries. But despite the simplicity and nice interpretability, these models are not useful if you have data that intrinsically has a nonlinear structure. So for example, on the left hand side, you have a regression problem mapping x to y. It clearly doesn't, the data clearly doesn't lie on line, so a linear model will give a very poor fit. Okay. Likewise, on the right hand side, we have a classification problem where we have data from 2 classes, red and green, and clearly, if you try to learn a linear classifier, it will do horribly on this data. Okay. So clearly, we need models that can capture the nonlinear structure in the data somehow. Now, can we use whatever knowledge we have about linear models to solve these problems? So that is what we will try to look at in this talk. Okay. So firstly, whatever we know about linear models, is that knowledge useless? Well, the answer is no. We can use pretty much what we know about linear models, and with some tricks, we can actually make those models still useful for these nonlinear problems. Okay? Yeah, so let's get started. So, it's back on. Yeah. Yeah, so just to give you a sort of a motivation as to how this trick that I'm going to talk about, the kernel methods, works, let's consider a very simple problem of classification where the goal is to classify these two set of points, green and blue, and we would like to learn a classifier that separates, like given a new point, whether it's a green class or a blue class. Okay. Now, do you think a linear classifier will work on this data? So can I learn a linear classifier that will separate the green points from the blue points? Most likely not, because you can see that the blue points lie within this, like these 2 groups of green points. So we can't really learn a separate linear hyperplane that will separate this data. This is a very cooked up example, very simple one-dimensional set of inputs. But clearly a linear hyperplane will never be able to separate this kind of a data. However, let's try to change the representation in which we have the data. So for instance, right now the data in this case is lying on a one-dimensional line, okay, real line. So suppose we take every point, let's say x, and map it to a 2-dimensional space. So suppose we have this x and we map it to something called a z, which is now defined by 2 coordinates, where the first coordinate becomes is x and the second coordinate is x squared. Okay, so with every x we are now converting it into a 2-dimensional point, x comma x squared, which will make the data look like this. Okay, because for every x you have z1 and z2, right? So originally the data was x, now we have z1, z2. z1 is equal to simply x, z2. So note that the x coordinate of each point is the same as the original coordinate, and then y coordinate is now x squared. Now the data lives in 2 dimensions. So originally it was living in 1 dimension, now it's living in 2 dimensions. Now with this representation, can we learn a linear classifier that separates the data? Clearly yes, because you can see that I can put a line, a horizontal line parallel to the x-axis, and that will separate the data. Great, right? So this simple trick of taking the original data and converting the feature representation of the data allowed us to reuse our linear models, okay? Although in 2 dimensions now. It's not 1-dimensional hyperplane, it's a 2-dimensional hyperplane, but still a hyperplane nevertheless, okay? Let's look at another example. So the previous example was for classification problem, predicting a class for an input. But we also know how to do regression, right? Linear regression, x to y, where y is a real valued number, okay? So let's look at this example. Again, we have x as inputs, y as outputs, and suppose we are trying to learn a linear, regression model. Again, the linear regression is basically fitting a line on this very simple example. Clearly, the data doesn't, it has sort of a linear trend, but it's not exactly linear. You can see that there are some non-linearity in this relationship. So clearly, linear regression will not do very well on this data. However, we can play the same trick that we did in the previous case. We can take every x, and now we can convert this x into a 2-dimensional vector, where the first coordinate is given by z1 and the second coordinate is given by z2. Okay. Now, with every x, we are replacing it by z1 and z2, where z1 suppose is simply x, and z2, the second coordinate, is cosine of x. I'm just like defining this mapping. It doesn't have to be predefined, but let's, for the simplicity, we'll just define these mappings. So suppose with every x we convert it into z1 and z2, then our inputs become x comma cos x. So this is my feature vector that you might, so you know the term feature vector, right? So our feature vector becomes x comma cos x, and y remains y. So y is the quantity that we want to predict. The nice thing about this mapping is that now the relationship between the new version of x, which is z denoted as z1 comma z2, and y is linear. So now I can fit in this simple, again, cooked up example, you can see that there is a linear hyperplane that can be fit on this regression problem. Okay. So again, originally the data was not linearly, it didn't have a linear structure, but just the simple mapping allowed us to still use a linear regression model in 2 dimensions to fit a model on this problem. Okay, so now we can learn a linear regression model with this new representation of the data. Okay. Now, in general, so this trick is not specific to these kind of simple examples. You can have a very general approach where you can take some data, let's say x1 through xn, a bunch of inputs, and you can try to come up with a mapping function phi. So I'm denoting this phi as a mapping function that transforms the data into some nice space where you can apply linear models conveniently. Okay, so in this case, the phi, this notation simply denotes that phi takes, let's say, some input. In this, again, simple case, I'm assuming that the input is in 2 dimensions originally, and it's mapping the inputs to 3 dimensions, okay? So again, this is still a kind of a cooked up example. So suppose I have data that looks like this. Again, it's a classification like problem. So we have x1, x2 as being the 2 coordinates, 2-dimensional data, and then we are defining another mapping, z denoted as z1, z2, z3, where each coordinate is defined in terms of the original coordinates. So z1 is x1 squared, z2 is square root of 2 times x1, x2, and z3 is x2 squared. So in this case, the original data 2-dimensional became 3-dimensional, and again you can see that in this simple classification problem, the data does become separable linearly. Okay. Any questions? Yeah.
So it's like it is always true that we have to move to a higher order from a lower order to fit a linear regression model. It can be that we have to move from higher to lower.
Yes. So right. But again, so this is just for illustration purposes. In certain cases, it may happen that originally the data in, let's say, 2-dimensional space may be non-separable, but there may exist some interesting mapping so that you can bring the data to 1 dimension. It can still, so it can very well happen. But conventionally, when these models are defined, you think in terms of some mapping. It doesn't have to be necessarily high dimensional, but typically we assume that we are working in some. Yeah. Okay. Right. So again, the idea will remain. I'm just setting up the stage. So the idea will be to take the data from some original space, map it through some mapping phi, so that the data becomes separable, and we can, or it exhibits a linear pattern. Okay. The problem need not be classification; it can be regression or some other dimensionality reduction problem can also be there. So the idea is to take this mapping and then solve the problem in the new space using a linear model. Okay. Now note that in the new space, the models that we are learning are linear. However, they correspond to a nonlinear model in the original space, which was our the original problem. Now, I talked about a certain mapping. I'm saying that, well, if we can have a mapping phi, then the problem will become easier. We will be able to apply the linear models. Now, and this seems like, it seems like a higher dimensional mapping will be very useful here. But it turns out that not every mapping is useful. I'll give you some examples here. Now, for this case, the first case, as you can see, clearly this mapping helps because, suppose this is again the classification problem. The first mapping helps. I can learn a linear classifier. The second mapping also, it's not the same as the first mapping. I'm mapping each x as x comma mod of x. Okay, so again, this is separable. However, in the third case, I'm again having a two-dimensional mapping. I'm mapping x to x comma x. The first feature is x. The second feature is also x. Do you think that this data is separable linearly? No, clearly not. And the reason is that the mapping that we have learned, that we have defined here, it's a linear mapping. Okay, as opposed to the previous mappings where you can clearly see visually that these mappings are non-linear. You have some data and you are applying some non-linear transformation on the data so that now the data becomes separable. But this mapping is clearly, so the third mapping is simply z equal to 1, this vector 1, 1 times x. So, and this is a linear transformation, some matrix or some vector applied to this this feature x. So linear mappings will not help us in these problems. We essentially need non-linear mappings. Okay, like the one, so here clearly x comma x squared is a non-linear mapping, x comma mod of x is also non-linear mapping, but x comma x is not a non-linear mapping, which is why this transformation, even though higher dimensional, it will not work for this problem. Okay. Now the question is, how do we get these non-linear mappings? I mean, can I always think of a non-linear mapping for some given data set? Clearly, it seems like an impractical problem because the data set may be too complex. We may not know anything about the data. So can we somehow come up with good set of functions that will automatically give us these mappings? Okay. So how do we get these good non-linear mappings? Again, remember that the mapping has to be non-linear. Linear mappings will simply not work. Now, there are various ways of getting these nice mappings. One way that we will look at in the second lecture is to learn these mappings from data. Okay, so suppose you are given some data, it may be possible to learn an appropriate non-linear mapping that makes the data separable linearly, or you can do regression using a linear model. So that's the one approach. You can learn the mapping. The other approach is that we can use some predefined good mappings that are given to us by some nice family of functions, nonlinear functions. Okay, so that is the approach that we will look at in the first lecture. So the approach will be that we can use some predefined good mappings. Again, the mappings will be of the form that it will be like a function phi that will take an input x and it will map to map to a possibly higher dimensional version of x, which is denoted by z or z. Okay. Now, at this point, you might ask this question that I have to compute these mappings. I have to take every input and I have to apply phi on that, right? So I have to do this for every data point, and it seems like very expensive because even here you can see that I take every input x1 comma x2, I compute this mapping for every point, right? So there are two issues here. Firstly, I have to do these operations to get the new representation. Then the other problem is that in the new representation, the data could possibly be much higher dimensional. So if the data dimensionality is increasing, the cost will also be increased. So whatever models we are learning, number of features in this sense, it's increasing, right? So there are two obvious problems that are that this mapping suggests. This mapping computation is difficult, as well as working in this high dimensional may be very, very difficult. Okay. Right, so it seems like mappings help, but they may be problematic computationally. So that's the first impression that we are getting from looking at this problem. However, luckily, in many cases we do not have to explicitly compute this mapping phi. Okay, so what I mean by explicitly is that you would never have to compute these features. Let's say. You won't have to compute the values of the feature, so you would never have to carry out this mapping. This will be possible to do using something called a kernel function. So the idea is that in what we can do, given some data, we can define something called a kernel function, which is denoted by k. It takes as input two things, so xn and xm, these are 2 points, and this cheap, I'm saying that this is a cheap to compute function. I'll explain why this is cheap to compute. But the idea is that suppose we have this kind of a function k, which takes as input 2 points xn and xm, and suppose this function is equal to the inner product of the 2 data points in the new space phi. So note that this is the similarity of xn and xm in the new feature space that I projected the data to, right? So suppose we have k xn comma xm being equal to phi of xn transpose phi of xm. If we can get this kind of a function, which is easy to compute, then the moment I have this value, if I can compute the left hand side, then implicitly I'm computing the right hand side, okay? So it seems then in that case we don't really have to worry about computing phi explicitly, okay? So that is the point, that if we have a function k that is equal to this quantity, then if we have access to k, then we would never have to worry about computing phi explicitly, okay? Now, as you can see on the right hand side, we have data appearing as inner product, okay? Now, so this mapping will not always be useful. Now, suppose we have some machine learning model where the data in your learning algorithm only appears in form of these inner products. So suppose your data only appears as xn transpose xm, okay? So suppose your data only appears like this. Then, if I want to map this data to some higher dimensional space and do learning there, all I care about is working with this number, right? Working with phi of xn transpose phi of xm, and I know that this quantity is equal to this function that I'm defining, right? So if all I care about is terms of this form, these terms can easily be computed in the new space, and I know that there is a function k that will allow me to compute this quantity without having to compute phi explicitly, okay? So that is the idea of implicit mapping. So the point is that the moment I have a function like this, so many functions k have an associated phi mapping, okay? So the moment we define k, we already get the associated mapping phi, right? So if I'm replacing these terms by k, I'm implicitly using this phi mapping for this problem. So this function that I'm talking about, k, which takes as input two data points, is known as kernel function, and it, as you can see in this definition also, this function is some notion of similarity between the data points, because we know that dot products between points are notions of similarity. So a kernel function is also a notion of similarity between data points in the high dimensional space defined by phi, okay? So a kernel function defines a similarity between objects or between data points, not in the original space, but in the new space where you have mapped the data to. Right. Now, so as I said, with every kernel function k, you get a mapping phi in an implicit way. So let's see, so let's look at an example of this kernel function, and let's see what the phi mapping looks like for that kernel function. Again, for simplicity, we will assume that we have data in 2 dimensions. So let's say we have 2 data points, x, which is x1, x2, and z1, z2. So these are 2 data points, 2 inputs in 2 dimensions. Now suppose we have a function k that takes as input x and, I think this should be, I think there is a small typo. So this is just like, this is just z. Okay. So suppose I have a function k which takes as input x and z, the 2 points, and computes this quantity x transpose z squared. Okay, what is x transpose z intuitively? It's the similarity between x and z, Euclidean similarity, right? And squared means that it's simplifying. I mean, it's just like another operation on top of x transpose z. Now, x transpose z can be written as x1 z1 plus x2 z2 and then squared. If I keep on expanding this, so this can be expanded to this, right? And after this step, what we can do, we can try to identify whether this quantity can be written as the inner product of 2 vectors. Okay, inner product, like can I write it as something transpose something, something of x1, something of x transpose something of z. Clearly I can write it, I can just separate the terms, I can write it as an inner product of 2 3-dimensional vectors. The first vector being x1 squared square root of 2 x1 x2 x2 squared. Second term, identical form but in terms of z1 z2. Okay, so this kx comma z that I'm defining, the notion of similarity between two data points or the kernel function, can be written as an inner product of these two vectors. And then, so the first vector, note that it's just some transformation of the data point x. The second vector is the same transformation because the form is the same of the second point z. So I can write it as phi of x transpose phi of z, and this is nothing but an inner product or dot product. So we can clearly see that the same relation that we saw on the previous slide, that k of x1 comma x2 or xn comma xn can be written as the inner product of those two data points in the phi space. Okay, and that kind of implies that the mapping that, so we started with the mapping, so this green is the mapping that we started with, and we saw that with this mapping there is an associated feature mapping phi. Okay, so this says, but note that we did not define phi to begin with, we only defined k. We defined k as a function, and then we saw that this k corresponds to a phi mapping, right, in an implicit way. Okay, so this phi mapping will be of this form that we already have seen, square root of x1 squared square root of 2 x1 x2 and x2 squared. And then, so this kernel is defining the implicit mapping from the original space to this new space, right? And importantly, you don't have to carry out this mapping phi of x. The moment you define k, it automatically gives this mapping for kind of free. You don't have to carry out this mapping explicitly, because in most problems you would only be worrying about, as I mentioned earlier, you would only be worrying about terms like this. So in many models like support vector machines, you might have seen support vector machines in, right, or linear regression, if you look at the learning algorithms or the way predictions are made, the inputs only appear like this, right? So wherever the inputs are appearing like this, you can easily replace it like this, phi of x, xn transpose phi of xm, and we know that this quantity is nothing but the kernel. Okay, so that's the idea of kernel methods. Okay, so we don't have to predefine or compute phi, right? So note that we have to define the kernel function, right? But we don't have to worry about defining or computing the phi mapping. So that's the key idea. Okay. The other thing is that, as I mentioned, computing this kernel function. So I'm saying that, well, we did not compute phi of x, so which helped us because we don't have to worry about computing it for every data point. But if this computation of the kernel function itself is very expensive, then there is no point doing this, right? Because in computing this, if this itself is very expensive, then we might as well just compute the phi function, right? Now the point is that, as you can see in this simple example, as well as in many other examples that we will see later on, computing this k function is very almost as cheap as computing x transpose z, because in order to compute this function, I just have to compute x transpose z and then square it, right? Just this simple operation is actually letting me compute the inner product in this high dimensional space, right? So which is why I'm saying that evaluating this kernel function on any two data points is almost as cheap as computing the inner product of those data points in the original space. Okay, and if you are wondering what is the cost of x transpose z, computing this, it's just order of d if we have d many features in the data, right? So computing k is not expensive in general for this simple example, as well as some of the other examples that we will see. Most of the examples that we will see, actually the kernel function is always defined in terms of some function of x transpose z. Okay, so the cost of computing the kernel function is almost as is mostly equal to the cost of computing inner product or simple distance between data points in the original space, right? So I have some notation which is sort of a more formal. I'll probably skip this point. It's not super important here. The key point here is that in terms of the notation is that phi is the function that we are using. So kernel, this kernel is so k is the kernel function which takes as input two things, 2 points, and k is defined like this. So k takes two things and gives a real valued similarity. So this notation simply means that k will have two inputs, x comma z, and it will give a real valued similarity, which is the similarity between the data points in the new space. Phi will take an input x and it will map it to some new space. So this calligraphic f is the new space in which the data lives. This calligraphic x is the original space in which the data lives. Okay, so x to f mapping. So this is just the formal way of defining the mapping, because the mapping takes the data or inputs from one space to the other space. Calligraphic x is the original space of the data, and the calligraphic f is the potentially high dimensional space in which the data gets mapped to. Okay. There are a couple of other technical issues which I'll kind of skim over because we don't have that much time, but the idea is that this space, this new space F is also known as Hilbert space. Has anyone heard what? Yeah, so it's just a Hilbert space. The other question, so there are a few things that you need to think about when you are looking at kernel methods. One important thing is that I said that K can be a function, K is a function that looks like this, phi of x transpose phi of z. Now, does every function of this form, is every function of this form a kernel function? So that's a question. I can always define some mapping phi, right? And I can look at phi transpose and phi of x transpose phi of z. Will that make it will that make K a kernel function? Well, not quite. So there are some technical conditions that are required in order for this mapping to be to define a kernel function. These conditions are typically known as Mercer's conditions. Again, the idea is that I'll give a very high level overview of what Mercer's conditions is, and probably for this talk you only need to know that. The idea is that K is a function, right? So K is a function of two things, two inputs, x and z. The condition that you need on this K function to be a proper valid kernel function is that this needs to be a positive semi-definite function. Okay, so that's a technical condition which basically says that if you have this, so this is the function K of x comma z, two data points x and z. If this function satisfies this condition, which is like the double integral of this quantity, where you are multiplying by f of x and fz, for all x's that are kind of like, you know, square integrable, right? So if this condition, so note that the left hand side has to be non-negative. Okay, so if this condition is, if the kernel function K satisfies this condition, then we say that this is a positive semi-definite function, and then only the kernel is a valid kernel. Okay, now it turns out that many of the so most of the kernel functions that we typically use are, they fulfill this property. Now there is also a caveat or a condition that there are certain kernels that we use in practice that do not satisfy this criteria, but they are still used as kernel functions. But again, this is kind of a technical condition on kernels. Another thing that you should keep in mind, and that's kind of a very important property of these kernels, is that if you have a kernel, you can compose, or if you have multiple kernels, you can compose more interesting kernels using those kernels. Okay, and I'm listing some of the conditions here. So suppose you have two kernels, K1 and K2, two kernel functions, and if I look at the sum of those kernels, this is also a kernel function. Okay, so K1, K2, let's say there are two functions, let's say x transpose x and maybe x transpose x squared. I'm summing them over, and then, you know, that is also, so a direct sum of two kernel functions is also kernel function. A scalar product, in fact, scalar positive valued, so if I multiply a kernel function K by alpha, where alpha is some positive number, that's also a kernel. Okay, likewise, if I take two kernels and if I take a direct product of these two, then that's also a kernel. And even with these three properties, you can imagine constructing lots of other kernels. I mean, clearly, if sum of two kernels is a kernel, then sum of three kernels is also a kernel, right? Or a linear combination or a weighted combination. All sorts of combinations can be tried out now with these simple rules. So if you have, let's say, one kernel and maybe another kernel, they both are good. You can try thinking of combining them to get more expressive, you know, mappings for the data. Yeah, so these are some of the properties that are worth keeping in mind about kernels. Okay. So yeah, as I said, kernels can also be constructed by simply composing these simple rules to get more expressive kernels. Let's look at some examples of kernels. So we already saw this very simple x transpose z squared kernel, which corresponds to a simple, nice three-dimensional mapping for two-dimensional data. So first of all, what is the most simple or the trivial kernel? Well, that's the linear kernel. It will not do anything. It will not map data to any new space. It will keep the data in the original space. So that's the linear kernel, right? But just it still satisfies the properties of the kernel. So this is the linear trivial kernel. Mapping function phi is identity function. X goes to X. I mean, remains in X. Okay. There are also various other kernels, so something called a quadratic kernel, where you define it as the same kernel that we saw earlier, x transpose z squared, or you can add some offset to this. You can say 1 plus x transpose z squared. Okay. Note that again, this is some notion of similarity between x transpose x and z, right? But not only in the original space, but in some higher dimensional space. Right? So this is called quadratic kernel because you basically are computing x transpose z, the usual inner product similarity, and then you're squaring it. Quadratic means like power 2. Okay. You can generalize this. You can actually have a polynomial kernel of a certain degree d, where d is greater than or equal to 2, which will look like this. So x transpose e to the power d, again the same thing to the power d. So this is known as this is known as the polynomial kernel of degree d. Kind of a very, very popular kernel is the so-called radial basis function or Gaussian kernel, which is defined like this. So again, k of x comma z, note the form. It's exp of minus gamma, where gamma is some constant, times the squared Euclidean distance between x comma z, x and z, right? Again, why does it make sense as a kernel? Anyone? So why does it make sense as a kernel? I mean, in general, why is this a reasonable kernel? Does it satisfy the property of what a kernel is intuitively? What is a kernel? Similarity between data points, right? So why does it make sense as a kernel? Yes, right. In some sense, if let's say x and z are, let's say, so suppose if x and z are very, very far from each other, then what, and if suppose gamma is some reasonable value, what will be this k comma x comma z? If x and z are very, very far from each other. Okay, what is the maximum value that this kernel can take? 1. When will that happen? When x and z are almost very, very close to each other, right? So if 2 points are very, very close to each other, which means that they are very, very similar, then this kernel will give you a value 1, which, let's say, that's the largest possible similarity between 2 data points. On the other hand, if x and z are very, very far from each other, it will be close to 0, right? Which again makes intuitive sense, because 2 points far away from each other, they should have a very small similarity, right? So it's a very nice kernel. It gives you a scale like 0 to 1. 0 means very, very dissimilar, very, very far apart. 1 means like very, very close, right? So, and now we have this extra hyperparameter in this kernel, the gamma, which kind of controls. So in some sense, whenever you are using a kernel, you are looking at who your neighbors are, right? If you have a high similarity with your immediate neighbors and low similarity with the neighbors that are far apart, right? But how do you define how big your neighborhood is? Okay, so in some sense, you can actually use this parameter to control what you deem, who you deem to be your neighbors. Okay, so if let's say gamma is, let's say, very, very large, what will happen? Okay, so if gamma is very large, then you have exp of minus gamma times this distance, right? So if gamma is very large, then what will happen?
0.
Well, not always 0. So it will be 0. So if gamma is very, very large, then even for small values of d, the similarity will be 0. Which means that you are only considering points as your neighbors that are very, very close, right? So unless d is very, very small, so unless d is like very close to 0, this kernel will give you a 0 value if gamma tends to infinity, right? So you are kind of, if you use, so gamma can kind of define what you consider as your neighbors. So if gamma is very, very large, then you are saying that, well, I am very particular about who my neighbors are, right? I'll only give a high similarity with those those inputs that are in the immediate vicinity of mine. Okay, the moment something tapers off, or I'll so in some sense you can actually, this is nice control over what you define similar objects to be, right? So this is a nice feature in this kernel, that you can actually use gamma as a bandwidth parameter. So this plays a big role. So this is a hyperparameter of your, so in any machine learning algorithm, you have some hyperparameters to tune, and you can use gamma, you can actually tune gamma to define the right kernel for data. Because so this can control what you think of, what points you are considering in the neighborhood of any given data point. So this is actually a very, very popular kernel. This, so note that at some places you would see this notation where gamma is actually used as, you actually see 1 over sigma squared, inverse of it. So there the notion will be different. If sigma is close to 0, then it means like gamma is, gamma tends to infinity. So in that notation, if sigma is close to 0, then again it means that you are considering very immediate neighborhoods. Okay, so that's the RBF kernel. Now, in all these cases, as I mentioned earlier, the moment you define a kernel, it implicitly defines a feature map, okay? Taking data from original space to the high dimensional space. We have already seen examples of what the mappings would be in these cases. So X transpose Z, we saw that if X was 2-dimensional, x1 comma x2, then the mapping was 3-dimensional, x1 squared, square root of 2, x1, x2, x2 squared. What might the mapping look like for this kind of a kernel? Okay, so let's actually look at. So So one of the interesting things about this Gaussian kernel is that the mapping that this kernel corresponds to, the phi mapping, it's an infinite dimensional mapping. Okay. We will see why that is the case. So whenever you are applying a Gaussian kernel, whenever you are using a Gaussian kernel for some problem, it means that you are mapping data to this infinite dimensional space where you have potentially infinite many features for every input that you have in the original space. Okay. But that's the magical thing about the kernels, because you don't have to carry out this mapping, right? So infinite, if you have infinite dimensional space, you have to and if you have to compute every feature in that space, it's very, very expensive. But the nice thing about the kernels is, about this kernel is that you never have to worry about computing that mapping. All you have to worry about is computing this quantity, and computing this is as cheap as computing the inner product, because x minus z squared, it's just computing the Euclidean distance in the original space, not in the phi new space. Okay, so we'll see why this corresponds. I'll give you the construction which will show that this kernel actually corresponds to infinite dimensional space. Another thing that you should note regarding this kernel is that, firstly, it's so this Gaussian kernel is also known as a stationary kernel, and the reason why it's called stationary is that if you look at the definition of this kernel, the mathematical definition of this kernel, the value of the kernel only depends on how far the two data points are. Okay, so it does not depend on where the data points are located. Okay, so even if you translate the two data points to some other, so suppose there are two other data points that have the same distance, then it's the same value, right? So it only depends on the distance between x and z. It does not depend on what where x and z are located, which is not the same with these kernels actually. So these kernels will, if you translate x to some other place, x prime, and z to some, and by the same amount, the kernel function the value will not be the same. Okay, so that's another property of stationary kernels, where the kernel's value will only depend on the distance between the two data points. The other point that I was making is that most of the kernels have one or more hyperparameters which need to be tuned based on your data, and you have to do cross validation to select it. I believe cross validation in some form you have seen. So in this case, as you can see, Gaussian kernel has the gamma hyperparameter. If you are using polynomial kernel, then you have this d parameter, the degree of the polynomial. These are the parameters that you typically have to tune using some cross validation procedure. Now I'll show you this example.
Actually, stationary kernel in this case.
Sorry?
Stationary kernel means what is that?
Stationary kernel is like the distance. It only depends on the distance between the data points. So that's the stationarity property.
Non stationary, then how to define?
This kernel is not stationary. So the quadratic or polynomial kernel, they are not stationary. So the stationary kernel simply means that the value of the kernel function only depends on the distance between the data points. It does not depend on, let's say, so in this case it does not in the polynomial kernel case, polynomial kernel is not a stationary kernel, right? Because it's not in form of x minus z squared, right? It's actually x transpose z squared, or 1 plus x transpose z to the power something else. So stationarity simply means that the value of the kernel function only depends on the distance.
Is there any specific advantage of having this?
Well, there are some theoretical advantages, but in general, you can see that this makes intuitive sense, because if there is some translation of your inputs, right, and if every input is shifted by the same amount, you don't want this notion of similarity or the degree of similarity to change, right? So there are clear intuitive practical benefits of having stationary kernel. There are theoretical benefits as well, but that's kind of beyond the scope of this kind of a lecture. Okay. Yeah, so the point that I was making earlier is that the Gaussian kernel or RBF kernel, it corresponds to an infinite dimensional mapping. So let's actually verify that that's indeed the case. Okay. So let's look at the definition. This is the definition of an RBF kernel. I will show with a very simple 2 or 3 steps of algebra that this kernel corresponds to an infinite dimensional feature space. And the algebra goes like this. Again, for simplicity, I will assume that this gamma hyperparameter is 1, although this derivation will be valid even for any gamma. And moreover, I will assume that x and z are scalar, so they just have one feature. Okay, but again, this proof goes for higher dimensional x and z as well. Okay, so this kernel for case when x and z are scalar valued and gamma equal to 1 will start with this e to the power minus x minus z squared. I can expand it like this: e to the power minus x square e to the power minus z squared times e to the power 2xz, simple algebra. And then I can use the property of exp function. So note that the first two terms I have retained just like that, and then exp function can be expanded in this infinite series. Okay, so that you can. So some of you might remember, or even if you don't remember, you can take my word that this is the simple infinite series expansion of exp function. Note the form. So this is an infinite summation where small k goes from 1 to infinity. K is the small k denotes the number of the index in this summation. So 2 to the power k, x to the power k, z to the power k divided by factorial of k. The important point to keep in mind here is that every term in this summation contains both x and z, each raised to the power k. Clear? So this, everyone with me on this, right? Now I can clearly see that this. So here's the important thing. We have x and z appearing together, right? So in some sense we are computing some sort of inner product between x and z, right? X to the power k and z to the power k. I can clearly see that this, I can write it as phi of x transpose phi of z, right? Because I can take all the red terms together and put them in an infinite. So note that. How do we define inner product? Inner product is always a summation. So sum of let's say xi yi form of this, right? And here we have an inner product containing infinite many terms. So it clearly implies that the things that I'm taking inner product of, they are also infinite dimensional vectors. Okay. So we can think of this as phi of x transpose phi of z, where phi of x and phi of z both are infinite dimensional vectors. What do these vectors look like? Well, I don't even have to worry about what they look like. It will be something like, I can just separate it, right? So it will be something like x to the power 1 divided by factorial 1, x to the power 2 divided by factorial 2, and so on, and I'll multiply every term by exp of minus x squared as well. So this will be my phi of x, and then likewise I will have a term like phi of z.
In between that will be plus sign, summation.
Well, so when you take the inner product of two infinite dimensional vectors, so you take elementwise product followed by summation, right? So that is the definition of inner product. Right? Yeah. So this summation immediately kind of tells us that there is an inner product going on, right? And the quantity on which I am computing the inner product is phi, and that quantity is just by the definition infinite dimensional, because it's just two infinitely long vectors, which are each first of which is phi of x, the second of which is phi of z. They both have the same representation. In the form you can see that the first phi of x will be exp of x minus x squared times this infinite series. So this is not an infinite series, this is like infinite dimensional vector. The first component is this, second component is this. So each of these components is multiplied by exp of minus x squared. Okay? So everyone convinced that this kernel corresponds to an infinite, taking the data from some finite dimensional space and mapping it to a potential, in fact an infinite, not potential infinite, in fact infinite dimensional space in this case. Okay? Yeah, so which is why we say that RBF kernel corresponds to an infinite dimensional mapping. But again, the point I wanted to emphasize or re-emphasize is that we never have to worry about computing these mappings, right? We don't have to carry out these computations in order to use a Gaussian kernel. In order to use a Gaussian kernel, all we have to worry about is computing this quantity, which is pretty cheap, okay? Just e to the power minus x minus z squared. Okay? So we have seen what a kernel function is, what it does, what are some of its mathematical properties. So how do we actually use a kernel function in a learning algorithm to make, because what was our original goal? To take a linear model and turn it into a non-linear model. Now, as we saw, the kernel function gives us similarity between two inputs, x, let's say x and z, or xn comma xn. Now, if I am given n inputs or n examples x1 through xn, then I can compute something called a kernel matrix, which I'm denoting by capital K, where every entry of this matrix can be defined as the inner product of the phi versions of xi and xj, right? So think of this as a n by n matrix. N inputs, so kernel matrix will be of size n by n. Kij is the similarity between I and j in the new space that I'm projecting the data to, but without actually having to project the data explicitly. Just using a kernel function, I can compute this. So note that I never have to compute the right hand side. I just have to compute k of xi, xj depending on the kernel I'm using. Okay, so I mean, pictorially you can imagine that you have data in form of the examples by feature matrix, and then you apply this kernel function, and then you get this n by n kernel matrix, where each entry of this kernel matrix is giving you the similarity between the data points. Okay. Also note that the kernel, this kernel matrix will be a symmetric matrix, because k of xi comma xj is equal to k of xj comma xi. Right? So this matrix is actually a symmetric matrix. Okay. Another property that this matrix satisfies is that it has to be a positive semi-definite matrix. Okay, because the kernel function that we used was a positive semi-definite function. So if you look at this matrix K, then it actually satisfies. So how many of you have heard about positive semi-definite matrices? I guess most of you, right? So a positive semi-definite matrix is such that, you know, if you take a matrix K and if you compute Z transpose K times Z, where Z is any vector, then this is always non-negative. Okay, and you can easily verify that this property follows from the definition of Mercer kernels, which said that the kernel function that I'm using to compute every entry of this matrix is also positive semi-definite function. Okay? So this is firstly, K is a symmetric matrix, and also it's a positive semi-definite matrix. Okay. So another property of positive semi-definite or positive definite matrix is that if you look at the eigenvalues of this kernel matrix, they are all positive. Okay. In machine learning, it's K is on the kernel matrix is also sometimes known as Gram matrix. Okay, so that's another name. You might see Gram matrix at some places. Okay, so this simple illustration shows that given some inputs, you can compute a kernel matrix, and then the question is that how do we use that kernel matrix in our linear models? Okay, because that's our original goal. Okay, so again, the idea was that we computed the kernel between data points to get these pairwise similarities, and then, so here is the application case of kernel methods. As I mentioned earlier, kernel methods can be used wherever you have a machine learning model where the inputs only appear in form of inner products. Okay, because that is where you can simply take the inner product X transpose, let's say Xn transpose or Xi transpose Xj, and you can immediately replace by so the idea to non-linear, so if you have a linear model where you have some inputs, each input appearing in this form, Xi transpose Xj, and you want to non-linearize it, right? What will non-linearizing mean? Well, it will simply mean that take every X, replace it by phi of X, okay? So that's the non-linearization operation. Now by the magic of kernels, we can simply say that this inner product in the phi space simply corresponds to the value of K of Xi comma Xj, which we can compute easily. Okay, so that's so this procedure is known as kernelization in machine learning, where the idea is to take any machine learning algorithm, identify whether the algorithm only requires inputs in form of inner products, and then replace all those inner products by this kernel function. Okay, so that's the one-line summary of what kernelization or kernel methods are. Okay. Yeah, so all you have to do is think of your machine learning algorithms like linear SVM or linear regression, and if you see that the inputs only appear in this form, you can just replace every occurrence by this thing, which is equal to K of Xi comma Xj. Okay. So in fact, many machine learning algorithms that are linear can be easily made non-linear using this trick. So here are some of the examples. So any method that only relies on computing distances between data points can be kernelized. Okay, why? Well, because distances can always be represented in form of inner product. So if I have, let's say, nearest neighbors, I guess you all know, right? So nearest neighbors, you have to compute distances between data points, right? X, let's say you get a new input x star, you have some training input xi, so you have to compute this distance. This distance corresponds to xi squared plus, x. So this x star is my test input, xi is one of the training inputs. So I can expand it like this, minus 2 x star transpose xi, right? So this is what the distance computation will expand to. And then what is this quantity? So this quantity I can easily kernelize. I can simply say phi of x star transpose phi of xi. I can do the same thing for these quantities as well. I can simply say that it's phi of x star transpose phi of x star. Okay, so wherever I am computing a distance, I can easily kernelize. So the inputs need not appear in form of inner product. They can even be appearing as distances, which translate to inner products anyway. Okay? So any method that requires on computing distances, you can replace that method by a non-linear kernel, and that will non-linearize your model essentially. Right? Something like, I'm not sure if perceptron was covered here, but again, it's another linear model where the data only appears as, or at least whenever you are learning the algorithm, you only have inputs interacting as inner products. So all those occurrences can be replaced by this kernel version of the inner product. SVM, I believe, was covered on day 1. So again, I'm curious, was kernels covered in that class? So so was this stuff new, or? somewhat new. Okay.
For new, I mean, there is a different perspective.
Right, yeah. So, but again, in SVM, what you might have seen is that you have something called a quadratic program. So, I'm not sure in what level of detail SVM was covered. I'll anyway show.
For understanding the subject, he has.
Yeah. So I'll have an example to show why SVMs can be easily turned into nonlinear models. Linear. So I'll show some brief examples of how we can take simple models like SVMs or linear regression, and then we can use the kernel trick there. I already showed you this simple example that if wherever you're computing distances in some model, you can easily kernelize those distances. Okay. So these methods are supervised learning models where you are trying to learn a mapping from X to Y. Right? But the idea of kernels, where you take a linear model and turn it into nonlinear model by applying a kernel, it also applies to unsupervised learning problems. For instance, if you are solving a problem like clustering, k-means clustering, again k-means all you're doing is distances, right? So I can take the k-means algorithm, I can replace all the distances by the kernelized version of the distances, and that immediately becomes a kernel k-means algorithm. Okay. Likewise, if you are doing something like principal component analysis, which is a dimensionality reduction method, even in a PC algorithm, you can see with some algebra, you can see that inputs only appear as inner products, and you can just replace all those inner products by the kernel version of it, the inner product. Okay. So most of the learning algorithms that we know about, at least the linear ones, they can easily be non-linearized using the idea of kernels. So, okay, so this is what I have as planned. I'll show a very a quick overview of how we can kernelize the SVM and how we can kernelize the ridge regression model, which is a linear regression model with L2 squared, regularization. I hope linear regression was covered. The X transpose X inverse X transpose Y model. So I'll show very simple, examples of these two cases to see how we can turn linear SVM into nonlinear SVM. Now again, in a single lecture, I can't really get into the details of what SVMs are. I believe you have already seen it. The key idea, so SVMs are large margin classifiers where the idea is to separate the classes by a sufficiently wide margin. The final objective function, because SVM finally turns into an optimization problem that you have to solve. The optimization problem of an SVM looks like this. Again, don't worry about the equation too much. I'll explain what the terms are. So you can see that is this form familiar to? I'm just curious. So did you see this form in the lecture?
Yeah.
Okay. So this is nothing but a quadratic program. In terms of a bunch of variables alpha, these are the Lagrange multipliers that you use in the SVM optimization problem. The important point to keep in mind is that in this objective function, where does the data reside? This is the term. So you have this. So this is the quadratic function because it's alpha is the variable that you are trying to optimize. It's a quadratic function in alpha, which is why it's called a QP, quadratic program. The data appears in this term G, okay, where G is an n by n matrix. Okay, so if you have n training examples, then this G matrix is an n by n matrix, where each entry of G is in this form. Yn and ym are labels, the binary labels, assuming we are doing a binary classification problem. And so it's ym times ym times yn times xm transpose xn. So this is what this G looks like, every entry of G looks like in an SVM problem. Okay, you can go back and check that this is what SVM objective looks like. Now, in the objective function, the data looks like this. Clearly, the inputs x only appear in form of inner products. So I can simply take this xn transpose xm and I can replace it by, so suppose I have some good kernel, let's say RBF kernel, I can simply say that let's assume that the data was being mapped into the representation, and then I can simply replace this quantity by k of xm comma xn, and that will immediately make my kernel, my linear SVM into a nonlinear SVM. So that's all that is required. You take the problem and this just one line of change. So this kind of shows the simplicity of the approach, that you take whatever, suppose you have a solver, you have an optimization solver for this problem, which takes as input G, and suppose you don't know about kernels, then you can only solve this problem where G can only be defined like this. But now that you know about kernels, you don't have to do anything new. All you have to do is replace this term by the kernel version, right? You say that it's yn times ym times yn times k of xn comma xm, which is easy to compute, right? And just that single line of change will make the model non-linear now. Okay. So whereas the typical linear SVM will only assume linear, separation boundaries, this nonlinear classifier will help you solve problems where you may have potentially nonlinear boundaries, right? So suppose you have something like this, you can actually with the SVM you can actually learn these nonlinear boundaries. Okay. So which is why SVMs are very, very popular. SVMs are not popular because they can solve like just a large margin. They can also be kernelized easily because the form of the objective function has a very convenient structure where you just have inputs appearing as inner products, and you can very easily kernelize it using the idea of kernels. Okay, so that's what I was talking about. Simply replace this term by the corresponding term where each inner product is replaced by the kernel evaluation. And then you have to do nothing new in order to solve the problem. You will solve it exactly the same way as you would solve the linear SVM problem. Okay, it's just that the definition of G matrix has changed slightly. Okay, and as I mentioned in the beginning, this will correspond to, so if your original SVM solves a linear problem, you can now use it to solve nonlinear classification problems. Right, so this is what SVMs are. I'll make a couple of other notes. So this is about the training. So this is note that this is training, right? You're training the model. You learn the model, and then you also have to make predictions, right? So that's in supervised learning, we don't just care about training a model using some training data. We eventually have to make predictions on some future data. We get a new X star, and we have to predict what the label is, whether it's positive or negative. Okay. Now that we are using the kernel technique, how do we make predictions? If a new data point comes in, now it might seem like if I get a new data point, I have to map this data point to some space, right? To the same space, and then only I can make the prediction. Okay. It turns out that we actually don't have to do that. So the idea is as follows. Firstly, for SVM, again, I'm not sure if this part was covered in the previous lecture, but for the SVM, the solution of so SVM learns a classifier, right? That separates the classes, and the classifier is in form of a weight vector. Okay, the weight vector that is like the normal pointing toward the positive class. So this is the weight vector of SVM, the solution of SVM, and the weight vector of an SVM has the following form. So you can say that the weight vector, which is assuming that you have d-dimensional data, the weight vector has the following form. It's alpha n times yn times xn. So the weight vector of an SVM looks like a linear combination of all the n inputs, where each input has an importance weight alpha, which is nothing but the solution of this SVM objective problem. So this alpha vector that I'm optimizing over in the SVM objective function is actually with every input, training input, you have an alpha n. Okay, and that alpha n is actually used in the final solution. So the SVM solution looks like this. So if the SVM solution looks like this in the original space, what will it look like in the new space? Well, I simply have to replace x by phi of x. Clear? So my weight vector of SVM in the new space can be represented like this, identical to how I represent the solution in the linear space, but in this version. Okay. Now there's a subtle point here that you should keep in mind, that if let's say x is finite dimensional, suppose x is d-dimensional, I can compute and store w, right? So if x is d-dimensional, what will be the dimensionality of w here? D, because it's just a linear combination. What about the kernelized case, when I am mapping the data by some kernel k to some infinite dimensional space? In that case, my weight vector of SVM will be in this form. If I'm using let's say RBF kernel, what will be the dimensionality of w here? Infinite, right? Because phi is now infinite, so w is infinite dimensional. Right? Now there is no way I can store this weight vector. Right? I mean, I could store it in using just d numbers in the linear case, right? I can't do the same thing in the nonlinear case. If I'm using a kernelized nonlinear version of SVM, I can't store this weight vector in form of d numbers. Okay, so does it mean that I can't use this model to make, because I need w in order to make predictions, because I make predictions like I compute w transpose x and I look at the sign of this, right? So that's how I make predictions for a linear model. Now if I can't compute this quantity, how would I make this prediction for a new input, let's say x star? Any suggestions at this point? Okay, so it's actually straightforward. So it turns out that even though we can't compute and store w, we don't actually have to compute and store w. If we can just store the data points with us, we can compute this quantity even in this new version of w. Okay, and the idea is as follows. Okay, so I told you that the prediction is made like sine of W transpose X. So in the kernelized version, what will the prediction look like for a new test point? It will look like this. So suppose I get a new test example, I'm calling it X, okay? And this B is the bias of SVM, which I'm ignoring. The prediction is Y is sine of W transpose phi of X, because X also has to be mapped to the same space, phi space, okay? That's my prediction, okay? Now it seems like, I have to map phi, map X via phi first, but that's not the case actually, because I already have W in this form. What I'm computing here, I'm just computing W transpose phi of X. This is simply this. I'm simply plugging in the definition of W, and then I'm taking this inner product with phi of X. Clear, right? So now this is not a problem, because all I have to do is compute inner product of each of the training. So these are the training points. I just have to compute the inner product of phi of xn, where xn is one of the training points, with phi of x, where x is my test point. And each of these phi of xn transpose phi of x can be replaced by the kernel k of xn comma x. So it's actually not that much of an issue. In order to compute this, I just have to compute the sign of this quantity, sigma alpha and yn k of xn comma x, right? So it's actually possible. So we never have to carry out this mapping phi of x explicitly. We could actually just use the property that phi vectors products are kernel evaluations. We can just compute this quantity. Okay, everyone with me on this? Now there is one caveat or small thing that you should keep in mind, is that you should also keep in mind the cost of this operation. Okay, so that kind of because the cost of this operation scales in the number of training inputs, right? Because you have to compute this n term and then these n terms and then compute the summation. So if you look at the complexity of this operation, how much time it takes, to make the prediction for every test input, it's order of n, where n is the number of training points, right? Whereas if you had a linear, so this is kind of the extra price that you are paying if you're using a non-linear model, because nothing comes for free, right? So you are using a richer model, so you would have to pay some extra price in order to make this better prediction, right? Whereas if you only computed, let's say, a linear model and computed extra W transpose X, the cost of this is just order of D, okay? Where D is the number, so in fact this is order of ND, because you have n inputs and you have D dimensions for each input. So the cost of this operation is order of ND. Whereas if you had a linear model, then computing the prediction sign of W transpose X is just order of D, because this inner product W transpose X is just order of D computation, right? So it kind of suggests that we have linear models are faster to make predictions on. Non-linear models like SVM, they actually depend on, since the prediction depends on every training input, they are slower in making prediction. Okay. Now, if you have seen things like nearest neighbors prediction, that's kind of similar, because in nearest neighbors also you get a test input, you have to compute the similarity with every training input, right? Then you take some majority vote, right? Something like this is going on here as well, because even the kernel SVM, as you can see, so this is a nice connection to see that the way kernel SVMs make prediction, the non-linear SVMs make prediction, is by looking at the test input and computing its similarity with every training input, right? And then weighting that similarity by some number alpha n, and then making a prediction. So at some level, the nonlinear kernelized SVM prediction mode is similar to how we make predictions in a nearest neighbors method. Okay, so that's kind of a neat connection, and it's actually so this is because kernel SVMs depend on similarity, right? And so do nearest neighbor methods. And this is the key point that you should keep in mind, that the prediction cost is slightly more expensive in this case. Now there's one more thing that you should keep in mind. So in SVM you might have heard about the notion of support vectors, right? Now in SVM, one of the nice property of SVM is that the alphas are the values of, it's kind of importance of every training input, and very few of the alphas are actually non-zero. So so you have alpha as a vector of size n, right? So alpha 1 through alpha capital N. Now this vector is n dimensional. Most of the entries in this vector are 0. these alphas are only non-zero for support vectors. So the claim that I made earlier is that the cost of this operation is order of nd. It is not nd, but order of the number of support vectors times d, right? So because in this summation you don't have to worry about any of the terms for which alpha is 0. Okay, so it's actually faster than order of n. It's like order of nd, right? It's actually order of number of support vectors times d. Okay, so which is why if you can get if you have, let's say, two solutions for SVM in which in the first one you have fewer number of support vectors, it might be preferable because it's kind of a simpler solution. It will make you predict faster. Okay, so that's the, so this is like this scheme is showing how you make predictions using kernel SVM. So as I said, in kernel SVM, one of the fundamental differences is that W cannot be explicitly stored because phi could potentially be infinite dimensional. Okay, let's say on the other hand, if you, let's say phi is some finite dimensional vector, then you can store W and then you can make predictions the usual way. Right? But as for most interesting kernels, phi is actually very, very high dimensional. So you don't worry about you don't have to store W. You just simply use this approach to make prediction. And that is another reason that, you know, if you are using kernel SVMs, you have to keep the training data at test time as well, because you can't just store W and, you know, throw away the training data, right? You have to keep the inputs, training inputs in memory, at least for the support vectors. You have to keep the support vectors in memory so that you can use those at the test time to make predictions. Okay? Yeah, so that's the idea that I was talking about, and I already made this point that the prediction cost of SVMs scales in the number of training inputs, or to be more precise, in the number of support vectors. Okay, whereas in the unkernelized version, W can just be written like this summation, where X is finite dimensional, and so you can just store W and forget about what your training inputs are, which you can't do in the nonlinear case. Okay, so everyone, any questions on the kernel SVM? Okay, great. So let me very quickly show another example as to how you can kernelize another very popular model, namely the linear regression model, Y as W transpose X, the simple linear regression model. Okay, so I will consider the special case, a variation of linear regression, the so-called ridge regression, where the idea is that we want to learn a linear regression model, Y approximately W transpose X, plus we would also keep a regularizer. So everyone has seen the notion of regular. So we will just add a regularizer of the form W transpose W, which controls the overfitting in the model, right? So we will have a squared loss of the form Y minus W transpose X for every training point, plus we will have lambda times W transpose X, W transpose W. So that's the objective function in linear regression. Now you might be wondering, you know, so can I apply a kernel model for this problem? Firstly, let's recall the fact that in order to kernelize an algorithm, we need the inputs to be in form of inner products. Okay. Now, just looking at this definition, it may not seem obvious that I don't have X appearing as X transpose X. Okay. But as I will show soon, it actually is the case. You know, after some algebra, you can actually show that the inputs only appear as inner products. So let me go over that algebra. Firstly, just the quick recap of ridge regression. Ridge regression looks like this: n inputs, squared sum of errors, plus the L2 squared quadratic penalty. Solution looks like this: W, the weight vector of the regression model, is X transpose X plus lambda I inverse X transpose Y, where the X transpose X is a D by D matrix. So I'm assuming that X is n by D here. N inputs, D features, and this is now we are no longer in the classification regime. We are solving a regression problem now. Okay, so this is the solution of a ridge regression problem. Now, how do we kernelize this problem? Okay, now it seems like so looking at this solution, do you think the inputs appear as inner products? How many of you think that inputs appear as inner products here? Raise your hand. Inner product means that each input or any two inputs should appear as in form of Xn transpose Xm. Do you think this? So this is for every pair of inputs. Here we have this big X transpose X. Do you think this is the same as this? Not quite. Even though this looks like X transpose X, this is not an inner product. This is actually a D by D matrix. So if you expand this matrix, each entry will not be of this form. So this X transpose X is a D by D matrix. But we will do a simple, algebra, and then we'll actually see that it's actually the case. So in this native form of this solution, it's not the case that inputs don't appear as inner products, but They actually do. So again, I'll make use of this interesting lemma which says that if you have an inversion of this kind, so we have a matrix inverse here, x transpose x plus lambda I inverse. So this thing, again, you don't have to worry about this result as such. This is a standard result that you can replace this inversion by an equivalent expression which will lead you to this expression. So the same W that I wrote here, x transpose x plus lambda I inverse x transpose y, can be rewritten as this. W as x transpose, now we have x transpose plus lambda I n. This is an n dimensional identity inverse I. So this blue term, which is a d-dimensional vector, and this red term pre-multiplied by x transpose, they both are equivalent if you apply this equation here. Okay. So the ridge regression solution that you popularly most often see like this, x transpose x inverse x transpose y, can also be written like this. You can verify that this is also d-dimensional vector. Now why is this form nice? Well, this form is nice because now this x transpose, can anyone tell me what is the size of x transpose? If x is n by d? Yeah, so x transpose is an n by n matrix, where each entry of this matrix is nothing but xn transpose xm. Because x transpose, you can easily verify that if you multiply, each entry will be inner product of two inputs. So I can replace every inner product by the kernel version, k of xn transpose x, k of xn comma xm. Okay. But we are not yet done yet. We also have this x transpose in the beginning. Okay. How do we handle that? Because I can't replace that x, because in order to kernelize, I also have to replace x by phi of x, right? Every input has phi of x. But we don't have to worry about that because we don't actually care about W. We care about making predictions where we'll get another input x and we'll take an inner product of this W transpose x, because we will have to actually do W transpose x for some new input x, right? So this x is left alone, right? We can't kernelize it. But the point is that when I'm making a prediction, I get a new x. Then with these x's, I have something else to take inner product with. Okay. Then I'll just kernelize that term. So just to make the idea more concrete. So firstly, again, this is kind of like not super important. One of the nice things about this solution is that with this solution, you can write W as a linear combination of the set of inputs that you have in the data. This is identical in the form that you had for the case of SVM. W is just this. You can represent this W as alpha n times xn, because this whole red term is nothing but an n-dimensional vector which you can call alpha. Okay. So just like alphas we had in the case of SVM, you also have alphas in the case of, you can you can define an alpha in the ridge regression model as well. So I'll just let's skip over these details. It's not super important here, but the point is the fact that how we make predictions. Okay. So again, for prediction we have to compute W transpose x. W, we already saw that W is written like this, either this whole thing in red or simply sum of alpha n times xn. And if I have W written as alpha n times xn, the kernelized version will have alpha n times phi of xn. Okay, which then I will take an inner product. So and then how will I make prediction? Well, I'll do this, right? Y as W transpose phi of x. I'll play the same trick that I played with SVM. So I already have W defined like this. I multiply it. Again, I simply have phi of xn transpose phi of xm, right? So and then I just have to replace this by a nonlinear kernel. Right? So the same thing. I get a test point. I just my weight vector is already defined in form of this. I just have to take inner products, and I'm done. One of the things is that just like kernel SVM, again prediction cost here scales in n, because you have to actually, in order to make each prediction y, you have to compute this all this n summation. Again, this is like nearest neighbors, because in order to get the response y for a new input, you are computing its similarity with each training point and multiplying it by some weight of that input. So this is, again, kernelized ridge regression is very similar to how nearest neighbors predictions are. So in fact, nearest neighbors is such a simple method, but you can see that there are interesting connections of nearest neighbors with so many other more sophisticated looking algorithms. At some level, they all are relying on similarities of the test input with the training inputs, right? So that's kind of a unifying theme. So nearest neighbors is a very, very fundamental algorithm. You know? So oftentimes we just think that, well, it's such a simple, stupid algorithm, but in fact, you can see there are very interesting connections with so many other models, right? Yeah, so I'll just so I think we'll take a break of like 5 or 10 minutes and then we'll reconvene. But let me just mention a few things before we adjourn. Firstly, the idea, so how do you know what kernel is right for you, right? Because I defined a few kernels like quadratic kernel, polynomial kernel, RBF kernel, and so on. So typically this is a model selection or hyperparameter selection problem. So you have to try out several kernels. Let's say you have some cross-validation set, you have to try out and see which kernel works best. There is also a huge amount of literature on learning the kernel from data. Again, this is kind of beyond the scope of this lecture, which is why. So you can actually learn kernel for given data. So you don't have to do cross-validation. You can even do kernel learning. Okay. And another point that is kind of very important is that you can actually combine multiple kernels. A point I made in the beginning that you can take multiple kernels and just add them using some weighted combination, and that also is a valid kernel. So there is also a lot of literature on multiple kernel learning. There are lots of other probabilistic models, which is again beyond the scope of the class. Yeah, there are things like adaptive. So these are kind of advanced versions of kernels. If you are interested, you can look at some of these techniques. So the second, topic that we will look at today will be about the case when we don't want to use a fixed kernel. So in all these cases, we said that, well, we'll use an RBF kernel. Maybe we'll play with its bandwidth parameter, but still it will be an RBF kernel, or it will be a quadratic kernel. Right? So note that the moment we define or choose a kernel, it automatically defines the feature mapping phi, right? So this phi function is defined the moment from the definition of the kernel. Can we learn the right mapping from data? Okay, so that's what. So I mean, there are many ways to do that. If you can somehow learn the kernel, then you can actually you can learn. It's equivalent to learning phi. But we will actually look at another technique, the so-called deep learning techniques, which in some way they're not exactly kernel methods, but in some sense they also learn a mapping of data to some other space. But that mapping is actually learned. So you'll have a parametric model that will allow you to learn the mapping. Right, so we will talk about those things. So I think I already made some of these points earlier that kernel methods, they are very, very flexible. They can help us learn very sophisticated models and nonlinear models, but they also come at a price because the computations are a bit more expensive. At test time, you have to spend order of number of support vectors times operation, or even at the training time, you have to compute the kernel matrix. This K matrix has to be computed for every pair of points, right? So these computations can be a bit expensive, but nevertheless, as I said, there is no free lunch. So I mean, this is a sophisticated model. It's more powerful. So you have to, at some point, you have to pay that extra cost. Okay? And there is a huge amount of literature. So all these, the fact that the prediction scales in the number of training inputs or the number of support vectors, people have looked at various ways of making it, doing further speed up to these issues for these issues as well. So I think I'll stop here. Let's adjourn, and then next session we'll talk about the basics of deep neural networks. Again, I can't really get into all the technical details of deep neural networks, but I'll try to give a high level overview of what deep neural networks are and what they can do. Okay.